Welcome once again to my YouTube channel. Today we are looking into a topic in physics, density and Archimedes principle. The contents we are going to look into: 1. Density of thrust, Archimedes principle, principle of flotation, and relative density. Firstly, we are to take the density. Now, what's this very density? Density is a measurement of how tightly matter is packed. Mathematically, density can be defined as a mass per unit volume. I repeat, density can be defined as mass per unit volume. You can still term it as mass over volume. Okay, so in that case, we have density with the symbol rho as mass per unit volume. Now, the symbol of mass is M. The symbol of volume is V, which means density can be measured based on its unit. Mass is measured in kilogram. Volume is measured in meter cube. So you now see that the unit of density is kilogram per meter cube. Or you can still have its smaller unit as gram, as mass is also measured in gram. Per volume is cm cube. So you have the smaller unit as gram per cm cube. Now, how do you measure this very density? Now, it depends on the shape of the object, whether the object is regular or irregular. If the object is regular, use the balance and get the mass. You get the mass by measurement. You can use beam balance, scale balance, just take the mass of it. Then on the part of volume, because it's a regular shape, you can do calculation in order to get the volume of the object. For example, if it is square, you have length times width times breadth, you get the volume of it. Then divide the mass by the volume, you have the density. But if it is a regular object, then first get the mass as usual using balance method. Then after which, each volume can be obtained using a displacement curve. The volume of water, the very object when immersed in water, that volume of water it could displace is said to be volume of that irregular body. Okay, now let's look into calculation of density. So we have a question on the board. It reads, the density of 400 meter cube of palm oil was 0.9 kilogram per meter cube before frying and is 0.6 kilogram per meter cube after frying. Assuming no loss of oil due to spillage, calculate its volume after frying. Now, to solve this very exercise, solution to the question. Now, we have to write down the parameters here. The density of 400 meter cube, which means the volume of it is 400, of palm oil was 0.9 kilogram per meter cube. Okay. Now, the density before frying is 0.9. That's the density. Now we're going to use this density before. Okay. Now density before frying we have 0.9 kilogram per meter cube. And the volume before frying is 400 meter cube. So we have volume before frying as 400 meter cube. Then after frying, the density becomes 0.6, which means the density reduces. So the density after frying we have 0.6 kilogram per meter cube. Now, assuming there is no loss, calculate its volume after frying. Now, what's the volume after frying? Now, from the information given, assuming there is no loss after frying, meaning that the mass of that oil remained fixed throughout the experiment. Because if there is a loss, then the mass of it will no longer be the same with its initial mass, but the contents of the oil remained intact. So in that very case, we have the mass. We have the mass before frying equal to mass after frying. Then, if we have a formula for density as mass per volume, look at, we have the density as mass per volume, which means the making mass the subject will now give us what? Density times volume. Okay? So here, the mass before will now be equal to mass after. So mass before, we have density times volume. So mass before now becomes density before times volume before. That is the very formula now. Now we have mass after becomes density after times volume after. So at this point, we are now asked to find the volume after. Hence, we make VA the subject of the formula. Now we have to divide both sides by density of A. Divide both sides by density of A. Hence, we have the volume after to be density before, volume before, all over density after. Now, if we do the substitution of those parameters, we are going to have volume after now becomes density before, we have 0.9. 0.9. We have the volume before as 400. Then divided by density after. Here, density after is 0.6. Now, what's the volume after? Now, if we do the calculation, then we are going to get 600. Now, the volume is measured in meter cube, and that gives the volume after. That's the volume of oil after the frying. Now, let's look into another part, which is upthrust. You need to ask yourself the reason why certain things do happen in life. For example, someone is about pulling bucket filled water from a well. You immersed a bucket just to draw water from a well. Now, when the bucket has been filled up with water and that very bucket lies under the water, as you are drawing it up, it will be so easy to draw up such that you can even use one hand to draw it up. But the moment the bucket comes out from the water, it will no longer be easy to be drawn. Hence, you now make use of double hands. Meaning that there is a force that has assisted you the very time the bucket was underwater. That very force that aided you, hence pushing up that very bucket, such that the force we are to add will no longer be much. But the moment the bucket comes out from the water, its weight increases. Hence, you now have to add more weight, add more force. Such force that aided you then is what we call upthrust. That is the force of that very water in that very case. So the water possesses the force. That's the upthrust, aiding you to lift up the very bucket when the bucket is inside the fluid. So that's the upthrust. Hence, we define upthrust as an upward force exerted by a fluid in quotes, liquid or gas, on a body that is immersed in it. I repeat, upthrust can be defined as a force exerted by a fluid, in quotes, liquid or gas, on a body that is partly or wholly immersed in it. So it's an upward force, hence can be called buoyant force, buoyancy. Take for example, you have, let's say we have this as a spring balance. We have this as a spring balance. Now this has a weight. Probably we have it as weight in air. Okay. Now you want to immerse this body into this very water. Let's say we want to immerse it into this very water. Now you've got the weight in air using spring balance. Now, when this body is immersed, when the body is immersed, now the body is already inside the water. Hence, the weight, we have water here. Okay, let me term it liquid. Now, this is the weight in liquid. So the tension here measures the weight in liquid, while tension here measures the weight in air. Hence, this is the actual weight. Now, the moment the body was in air, its weight gives you its original what? Weight. But the very time it was immersed in this very water, the weight will lessen because there is an upward force. Okay, that very upward force is the force that aided or that aids you in lifting this very body. So in that very case, the upthrust now results as a difference between this very what? Weight in air and the weight in liquid. So that loss in weight is what we call upthrust. So to measure that very upthrust, we now have what? Weight in air minus weight in liquid. This gives you what? The formula to calculate the upthrust. Now let's solve exercise on this very upthrust. Remember, I told you that upthrust is an upward force exerted on a body that is wholly or partly immersed in a fluid. And as you can see now, the very upthrust here and the weight, these are the only what? Forces that exerted on this very body. While weight is acting downwardly, the upthrust is acting upwardly. So let's solve calculation on this. Okay, we have a question on the board. It reads, a body completely immersed in water has a weight of 40 Newton. When the upthrust of the water is 15 Newton, calculate the mass of the body. Now, solution to the question. A body completely immersed in water has a weight of 40 Newton. Hence, when the body was immersed, its weight is 40 Newton, such that we have the body in a fluid. The mass of this is what? Is 40 Newton, which means that the weight is 40 Newton, which means the weight they are talking of is the weight of that very body in liquid, which is WL. Hence, we have the weight in liquid as 40 Newton. When the upthrust of the water is 15 Newton, so the upthrust now is 15 Newton. We have 15 Newton. Now calculate the mass of the body. Now we are asked to calculate the mass of the body. Now, if you know the weight of the body, you can then get the mass of the body because weight is a product of mass and acceleration due to gravity. And here, the acceleration due to gravity was given in the question is 10 meters per second squared. So at this point, we have the upthrust from the formula is weight in air minus weight in liquid. Now, they have given us the upthrust. We have the upthrust here as 15. Weight in air, we don't know it. Then minus weight in a liquid, which is 40. Now, if you make WA the subject, which is weight in air, minus 40 will cross over. It becomes 40, positive. So the weight in air now becomes 40 plus 15 is 55. That's the weight in air. Now, because we've got the weight, to get the mass will be easy. Now, recall that we have weight equal to the product of mass and acceleration due to gravity. Now, if you make M the subject, you are going to have M equal to weight all over acceleration due to gravity. In that case, the mass becomes, weight in air is 55 divided by acceleration due to gravity, which is 10. So 55 divided by 10, you have the mass to be 5.5 kilogram. That answers the question. Now, we've done that of upthrust. Let's move into Archimedes' principle. So the Archimedes principle, now what this very principle is telling us is also related to upthrust. Now, when you immerse a body in a fluid, whether the body is immersed partly or the body is immersed wholly, you will observe that there will be a displacement of that very liquid. Now check, for example, we have this very displacement can. We have a displacement can. We have this body. We have this body. You are about immersing it. So we have this. Now this is the body. Then here is the liquid. Okay. Now the weight here, remember, is the weight in air, which means you have not immersed it already. Now, when this very mass, you have the mass. Now, when the mass is a mass in that liquid, so at this point, so look at, the mass has been immersed, so the weight of this very mass will now be what? The weight in a liquid. Now, the moment you immerse it, there will be the spillage of liquid. Okay? There will be overflowing of this very water, which will now pass through this very nozzle. Now, the water that was displaced, this is the displaced water. Okay? This is the displaced water or the displaced liquid. Now, if we are to measure the displaced liquid, if you are to measure its weight, you will observe that the weight of the displaced liquid and the weight of that very body immersed, that's the weight of this body, okay? The weight of it, which if you immerse the body, the weight of this liquid displaced will now be equal to the difference in weight between the body in air and the body when immersed in a fluid, telling you that the displaced water has a weight equal to the upthrust. And that's what Archimedes is all about. So Archimedes made a principle that when a body is partly or wholly immersed in a fluid, that the body has to experience an upthrust, which is equal to the weight of the fluid displaced. That states the Archimedes principle. I repeat, the Archimedes principle states that when a body is partly or wholly immersed in a fluid, it experiences an upthrust force, which is equal to the weight of the fluid displaced. So with this, the weight of the displaced liquid, if I should take it as WD, now we have the upthrust, which is equal to the weight of the displaced liquid. Now, the weight of the displaced liquid is the difference between weight in air and the weight in liquid. So you can also say that upthrust, in that very case, difference in weight. This is the very first formula we got. This is the very first formula we got. But with this upthrust being equal to weight, you know that weight is the product of mass and acceleration due to gravity. Now, if we are to substitute this very weight into this very formula now, you are going to have upthrust is equal to the product of mass and acceleration due to gravity, where this very mass is the mass of what? Displaced liquid. So at this point, you remember that density is mass per volume. Okay? Now, if we are to make the mass the subject in order to replace it here, you are going to have that mass is equal to rho v. Okay? Now, take this and substitute it here. You now have that upthrust is equal to mass, which is rho v times acceleration due to gravity. So this gives another formula for upthrust. Hence, we've generated two formulas for upthrust. Now, the upthrust is equal to rho vg, where rho is the density of the displaced liquid. Then V is the volume of displaced liquid, not the volume of the liquid in this very container, but the volume of that very liquid displaced. That's the meaning of V. Yg is the acceleration due to gravity, which is constant value, probably 9.81 meter per second squared, or approximately we have 10 meter per second squared. So that gives the upthrust. So we have two formulas to be used in solving upthrust. We have weight in air minus weight in liquid. We also have this very well. Remember, this is not a volume of the container here. It's not the volume of the body itself, but it is the volume of the liquid displaced. Okay, although the volume of the displaced liquid may be equal to weight of the body in air, but once we equate this weight displaced with that of weight in air, then we now talk about flotation. Now, once flotation, or the principle of flotation, states that when a body is immersed in a fluid, it displaces its own weight in fluid. Hence, if you say that a body is floating, it means that the weight of that very body will now be equal to the weight of the displaced liquid. As you are swimming water, you have to displace a volume of water which has the same weight with your own weight. If you could be able to do that, you will float. Flotation is like opposite of sinking. If a body does not float, we say the body sinks. So the only condition that will make a body to float is when the weight of the liquid you are displacing is equal to the weight of you. So your weight being equal to the weight of the fluid, then the tendency of you floating is 100%. So at that very point, we can now say the flotation, the principle of flotation states that the weight for a body to float, I repeat, the principle of flotation states that for a body to float, the weight of the displaced fluid has to be equal to the weight of the body. Principle of flotation is only obeyed when the weight of a body immersed in a fluid is equal to the weight of a displaced liquid. So this gives what? The principle of flotation. So we say that a body floats when the weight of that very body is equal to the weight of the fluid displaced. Let's do calculation on this. Okay, we have a question on the board. It reads, a solid of mass 1 kilogram suspended by a string is completely immersed in water. If the tension on the string when it is in water is 15 Newton, calculate the upthrust on the solid. 2, the volume of the solid. 3, the density of the solid. Now to solve the exercise solution, we write down the parameters. A solid of mass 1 kilogram. Now this is the actual mass of the body, which is 1 kilogram, suspended by a string, is completely immersed in water. Completely immersed in water. Note that very statement. If the tension on the string when it is in water is 5 Newton, that means the weight is 5 Newton when it is in water. That will now be weight of the body in liquid. So we have the weight in liquid to be 5 Newton. Now calculate the upthrust on the solid. Calculate the upthrust on the solid. Then we have G given as 10 meter per second squared. Then again, we have upthrust of water as 10 raised to power 3 kilogram per meter cube, which means 1000. Okay. Now, how do we get the upthrust? You remember I gave you up to 2 formulas now in upthrust. Now we already know the weight in liquid, but we don't know weight in air. But we know the actual mass of the body, hence we can calculate the weight in air. Now, because we've known the mass, if you now multiply it by acceleration due to gravity, it gives you the weight in air, which is the actual weight. So the weight of the object in air, which will now be mass times acceleration. Now we have the mass as 1, then times acceleration due to gravity, which is 10 meter per second. 1 times 10 will give us what? 10 Newton. Now we've got the weight of the object, which is the actual weight. Now, in order to get the upthrust, which is the very first question there, the upthrust is weight in air minus weight of the object in liquid. Now we've got the weight in air, which is 10 Newton. So the upthrust becomes 10 Newton minus weight in liquid, which is 5 Newton. So the difference will now give us what? 5 Newton. So we've got the upthrust. Now the second exercise there, we're asked to find the volume of the solid. Now, based on the statement, completely immersed in water. Hence, the body is completely immersed in water. When a body is completely immersed in a water, then the weight of the body, okay. Now, from the statement, completely immersed in water. When a body is completely immersed in water, the volume of the liquid or the water itself that will be displaced will now be the same volume with that of body itself. So the volume of a body immersed totally in a fluid will be equal to the weight of the fluid displaced. Take for example, when you get a body, you immerse it totally in a fluid. The very space of which the body takes is the volume, is the space of which that very the very body has. So the body has displaced water in order for it to take or to occupy that very area, that very volume. So that tells you that the volume of a body immersed in a fluid is equal to volume of a liquid that was displaced. So in that very case, to answer the volume of the solid, we said volume of the solid is equal to volume of displaced liquid. So how do we get the volume of displaced liquid? From the formula of upthrust, we said upthrust is rho Vg. Here is the density of the water in that case, and it was given. Now the volume of the displaced liquid, which will now be equal to the volume of the solid. So we now have the upthrust as 5 Newton. We have 5 here. Density is given as 10 raised to power 3. So we have 10 raised to power 3 means 1000. Then times volume. The volume is the one we are looking for. That's the volume of displaced liquid. Then times acceleration due to gravity, which should now be 10. So we have 10. So if we multiply this, we have 5. 10 raised to power 3 times 10 gives 10 raised to power 4. times V. So we have this. So in order to get the value of V, you divide by 10 raised to power 4. So VD now becomes 5 divided by 10 raised to power 4. And if you do that, you are going to have 5 divided by 10 raised to power 4 will give us 5 times 10 raised to power minus 4. Volume is measured in meter cube. That gives the volume. Then the next exercise there, remember volume of displaced liquid is the volume of solid. So you can now say that volume of solid is what? 5 exponential minus 4 meter cube. Then again, we are asked to find the density of the solid. Now, in order to get the density of a solid, density is mass per volume, right? Now, you've got the mass of the body was given, okay? Then what about the volume? We've got the volume. So, we have the mass, 1 divided by 5 times 10 raised to power minus 4. So, if you do the calculation here, you are going to have 1 divided by 5 will give 0.2, right? So we have 0.2. Let's finish it up here. Density is equal to 1 over 5 times 10 raised to power minus 4. So the density is 1 divided by 5. We have 0.2. Then times 10 raised to power minus 4 will now come upward. We have this. So if you multiply this, we are going to have 2.0 times 10 raised to power 3. Hence, the density is what? 2 times 10 raised to power 3 will give 2,000. Now, density is measured in what? In kilogram per meter cube. That gives the density. Now, let's move into relative density. So, coming to relative density, what's the relative density? Relativity. So, relative density is a measurement of density of a substance relative to the density of water. So water is taken as a reference here. So relative density mathematically is a what? Is the density of a substance per density of water. So we have it. The relative density is the density of a substance, the density of a substance to the density of water. The density of water. So, if I take this as the density of a substance, then this one becomes the density of water. And you know, the density from the formula is mass per volume. Okay? So, in that very case, when we compare the densities of different bodies, where we have mass per volume, we have relative density in that case. Density of a substance, which is mass of that very substance, per volume of the substance, right? Per volume of the substance, then divided by density of water, which is mass of water, divided by volume of water. Now, at this very point, you can get the relative density. If you change this whole multiplication, we have mass of the substance over volume of the substance times, this will now reverse as volume of water over mass of water. Now, let's take a case where the volume of water is equal to the volume of the substance. If the substance has a volume equal to that of water, that means V, let's take it as equal, Vs being equal to Vw, let's take it as V, they are now equal. So in that case, our relative density now becomes mass of the substance over volume times volume of the water over mass of the water. This will now cancel out. And if it cancel out, we have mass of the substance over mass of the water. So in that case, we are going to have relative density as mass of the substance over mass of water. This gives another formula for relative density. But in this very case, you remember that the mass in question will now be mass of equal volume of that very substance. So in that very case, we say mass of a substance the mass of a substance all over mass of equal volume of water. So it's not mass of any water, but it's mass that has the same volume with that of the substance. So we now have two formulas. Then again, if you are to introduce acceleration due to gravity, you get weight because weight is a product of mass and acceleration due to gravity. So from this very formula, where we have relative density as mass of a substance over mass of water. Now let's introduce G divided by G, which is acceleration due to gravity. If you cancel it out, you have 1. So we have relative density, mass of the substance times G all over mass of water times G. Now, mass times acceleration due to gravity, that is weight. So at that case, we are going to have relative density equal to weight of a substance over weight of equal volume of water. So we now have another formula there. So in that case, we now say that relative density is weight of a substance all over weight of equal volume of water, weight of equal volume of water. Now let's also look into the relative density of liquid, how to get the relative density of liquid, because these ones are majorly used when you are asked to find the relative density of solid. So let's get the formula for relative density of liquids. Okay, so we've derived 3 formulas based on density, relative density of a solid. The 3 we did or we obtained, we have relative density as density of a substance over density of water. That's the general formula there. Then we also get relative density as mass of a substance over mass of equal volume of water. We get another one. And the third one, we have the weight of a substance over weight of equal volume of water. Now, what about having liquids? Now, for the liquids, we have relative density of liquids. The relative density of liquids equal. First, we have to now consider maybe a particular substance. Maybe you now want to get a relative density of a liquid. Then you now get, for example, a solid ball. You immerse that very solid ball into that very crazy. It has to displace a volume of liquid which has a weight known as upthrust. Then get that same body, immerse it in water. It will also displace the same volume, which we now have weight equal to each word upthrust. So in that very case, you've got the upthrust in that very kerosene. You've also got the upthrust of water. Now, if you divide both, dividing the upthrust of that kerosene with that of water, you get the relative density. Hence, you can now say relative density of a liquid is the upthrust in liquid over upthrust in water. So that gives a formula. So in that case, we have a short formula here as upthrust of liquid over upthrust of water. Then again, the volume that was displaced by that ball in the kerosene will still be the same volume it will displace by that very water. So you can also say relative density of liquid being equal to volume of liquid displaced, volume of liquid displaced all over volume of water displaced by the same body, okay? Then again, you can also relate it with its weight. So we have the relative density of liquid being equal to weight of liquid displaced all over weight of equal volume of displaced liquid. Equal volume, weight of equal volume of water. So that gives the relative density. Now let's employ it in solving exercises. Okay? Okay? Oh, you can also include the mass. You can also include the mass. So you can also say it is mass of liquid over mass of equal volume of water. Okay, so with this, we are going to solve calculations. We have a lot of formulas, so don't allow those formulas to confuse you. The only thing you just need to know is to get the knowledge of it. You are good to go. So let's move into calculation now. So we have question on the board. The traits, calculate the density of seawater whose relative density is 1.024. You know, relative density has no unit. Why? Because it's a ratio of similar quantities. Density of a substance over density of water. Density of a substance is measured in kilogram per meter cube divided by density of water, which is also measured in kilogram meter cube. Okay, so to solve this very exercise, we write the parameters. Calculate the density of seawater. So we are asked to calculate the density of seawater. Let's say we have S, density of seawater. We represent it with this. So calculate the density of seawater. This is the symbol now. We are using this to represent the density of seawater, whose relative density. Now the relative density of that seawater is given as 1.024. Now we have the density of water given as 1000. So the density of water, we have it as 1000 kilogram per meter cube. So from the formula, relative density is equal to density of substance over density of water. That's the relative density of the seawater. So in that case, the relative density was given as 1.024, which will now be equal to relative density of the substance over density of water. Density of water now is what? Is 1000. So at this point, we cross multiply. So if you cross multiply, you have density of a substance, 1.024 times 1000. So if you multiply this, density of a substance now becomes 1024. Density is measured in kilogram per meter cube, and that gives the solution. Let's get to the next exercise. We have a question on the board. It reads, a solid weighs 10 Newton in air, 6 Newton when fully immersed in water, and 7 Newton when fully immersed in certain liquid X. Calculate the relative density of the liquid. We have the option A, 5 over 3, B, 4 over 3, C, 3 over 4, and D, 7 over 10. So, solution to the exercise. So we have a solid weighs 10 Newton in air. Weight in air, we have 10 Newton. 6 Newton when fully immersed in water. So weight in water, we have 7 Newton, we have 6 Newton, and 7 Newton when immersed in a certain liquid X. Then we have weight in a liquid X. We have it to be 7 Newton. So calculate the relative density of the liquid. Now relative density of liquid X, we're looking for its relative density. Now it will now be the upthrust of the liquid over upthrust of water. So in that case, upthrust in X, that's the liquid, will now be weight in air minus weight in X. X is the liquid, while the upthrust of water now becomes weight in air minus weight in water. So if we substitute this, we are going to have relative density of X being equal to weight in air minus weight in X, all over weight in air minus weight in water. So at this point, we have to do the substitution of the values. Weight in air is 10 Newton, weight in X is 6, weight in X is 7. Then we have weight in air as 10, weight in water is 6. So here we have 10 minus 7, we give 3. 10 minus 6, we give 4. And that gives the answer, no unit, remember, because we are talking about relative density. And that makes option C to be the correct option. So if what we did was able to help someone out there, please subscribe, share, and turn on notification for others to learn. See you on our next class.